In this video, we will see the need for the sampling theorem and how we can prove it in a graphical and analytical way. Here, we have a real-time analog signal, a smooth continuous waveform, just like speech, music, or temperature. But the computers cannot understand this continuous form. To make the signal usable in digital systems, we must sample it. The sampler takes quick snapshots of the signal at fixed time intervals. These samples are then sent to the analog to digital converter, where they are converted into a binary numbers through quantization. Finally, all these binary values together form digital data that the computers can store, process, and analyze. The sampling theorem tells us how fast we must sample so that the original analog signal can be perfectly reconstructed without losing information or creating errors like aliasing. That's why sampling is essential. It is a bridge that safely connects the analog world to the digital world.
Let's see the statement of sampling theorem for band limited signals. A band limited signal x of t can be reconstructed from its samples taken at a rate of fs greater than or equal to twice fm measured in hertz, where fm is the maximum frequency in the spectrum of x of t. Or we can also state in an alternative way, a band limited signal x of t can be reconstructed from its samples if the spacing between the samples is t less than or equal to 1 by 2 fm measured in seconds, where as usual fm is the maximum frequency in the spectrum of x of t. Before proceeding to the graphical or analytical proof, first let's understand what the band limited signal is. These band limited signals are also called as low pass signals. The word I am using, band limited or low pass, you can see some examples of the spectrum. Where x of omega, you can see that it is confined between the frequencies minus omega n and omega n. Or the spectrum can be just like a gate function, as usual, like between some limits of omega m and minus omega m. Or you can take any specific shape but confined to the limits of minus omega m and omega m, where omega m is the maximum frequency in the spectrum, which is measured in radians. Signals which have such spectrum, we call them as band limited signals, where the frequency is confined between some limits. Now, let's see the graphical and analytical proof of the sampling theorem. All this proof of the sampling theorem is well explained using the concept of Fourier transforms. So one should have the knowledge of Fourier transforms to understand this graphical and analytical proof. Assume that there is some continuous signal x of t and whose spectrum, which can be represented after the Fourier transform, which is band limited. Assume that the spectrum is x of omega for the given x of t, and it is confined between some limits of minus omega m and omega m, indicating that x of t is confined to some specific frequencies, which is the shape is the assumption here, and we call this as a low pass signal, or x of t can also be called as a band limited signal. The sample process can be done with the help of an impulse train. You can see I'm drawing the impulse train here. Impulse train in the sense it is a series of impulses which are being spaced at some equal distance and they spread over the infinite line limits. And this I am representing as delta suffix t of t, which is represented as a sum of impulses, sigma n equal to minus infinite to infinite delta of t minus n capital T, where capital T is representing the spacing between the impulses. For every capital T, we have an impulse. That is, capital T is a fundamental period of this impulse train. The sampled version xs of t is obtained by multiplying the continuous signal x of t with this impulse train. This is how the sampled version looks like, where the samples are obtained at the same intervals where the impulses exist. And the amplitudes of these impulses resemble the original signal. So that's why I'm drawing the dashed line for representing the amplitudes. You can see that xs of t, the sampled version after this multiplying x of t and delta t of the impulse train, represented as a series of impulses present at the mentioned time instance t, 2t, 3t, 4t and so on. As we have seen the spectrum of the original signal, let's see the spectrum of the impulse train. As we all know that the spectrum of the impulse train results one more impulse train, where the spacing between the impulses is omega naught and amplitude is omega naught. That's why it is represented as omega naught into sigma k over the infinite limits delta of omega minus k omega naught. That means we have impulses for every omega naught. The spacing between the impulses in the frequency domain is omega naught. And this is periodic, obviously. This is a magical result that an impulse train in time domain results one more impulse train in the frequency domain. which spacing is omega naught and amplitude is omega naught. And now let us see how the spectrum of the sampled version x s of t, that is x s of omega, obtained. We observe that in time domain it is multiplication. Obviously, in frequency domain it should be the convolution. That's why the result of spectrum of x s of t is a convolution between x of omega and the impulse train in frequency domain. Now let's see the mathematical representation of the spectrum of sampled version x s of t. It is represented as x s of omega, which is convolution between x of omega and the impulse train in frequency domain. X s of omega equal to x of omega convolution omega naught times delta omega naught of omega, which is equal to x of omega convolution omega naught times impulse train is represented as summation k over the infinite limits delta of omega minus k omega naught, which is equal to, since omega naught is a constant, so omega naught multiplied with k over the infinite limits x of omega convolution delta of omega minus k omega naught. So we have to perform the convolution between x of omega here and delta of omega minus k omega naught. Now let me apply the convolution integral. So integral over the infinite limits x of u delta of omega minus u minus k omega naught du. So as per the property of impulse function, so we can simplify it as omega naught and summation remains the same. Integral infinite limits. Since the impulse here exists at u equal to omega minus k omega naught, since u is a variable here, so impulse exists at u equal to omega minus k omega naught. So x exists at the same u, that is omega minus k omega naught. This is based on the property of the impulse function. Impulse exists and du. And here omega naught as usual, summation as usual, and x of omega minus k omega naught doesn't contain u, so it can be taken out of the integral, and inside the integral we have the impulse, the same impulse du. And since area under the impulse is 1, so the integral value takes a value of 1, and finally x s of omega is equal to omega naught into summation k over the infinite limits x of omega minus k omega naught. Here actually I forgot to mention 1 by 2 pi. I'll tell you why this 1 by 2 pi comes. So let me write 1 by 2 pi in each and every statement. And this omega naught by 2 pi, where I need to represent here, as you all know that it is equal to 1 by t. So xs of omega is equal to 1 by t times summation k equal to minus infinite to infinite x of omega minus k omega naught. This 1 by 2 pi is from the property actually, that is a frequency convolution property that I'm going to write here. That is the product of x1 and x2 in time domain. Its spectrum, that is a Fourier transform, is 1 by 2 pi times x1 of omega convolution x2 of omega. This is the reason I wrote 1 by 2 pi based on the property of Fourier transform. Xs of omega is derived. Now, based on this xs of omega, how this plot of xs of omega will be. And here we discuss about three cases while plotting this xs of omega. Now let's see the three cases. Case 1, what we say it as a critical sampling case. Now let me draw the xs of omega in this case. This red color spectrum which I have drawn here is a spectrum of the original signal x of t, and the spectrum which I am drawing repeatedly in a black are the repetitions of this spectrum observed in xs of omega, where this is obtained when k equal to 0. This is when k equal to 1, that is x of omega minus omega naught delayed by omega naught units. And this is at 2 omega naught. This is at 3 omega naught. This is at minus omega naught. This is at minus 2 omega naught. This is k equal to 2, where x of omega minus 2 omega naught delayed by 2 omega naught units. This is for k equal to 3, x of omega minus 3 omega naught. So all these are obtained from xs of omega only. This is k equal to minus 1, x of omega plus omega naught advanced by omega naught units. K equal to minus 2, x of omega plus 2 omega naught. So all these are the repetitions which are obtained from xs of omega for different values of k. These are all the repetitions for different values of k from k equal to 1 to 3. And also these are the repetitions for k equal to minus 1, minus 2, and so on. You observe that like original spectrum is lying in between minus omega m and omega m. And this distance for the first repetition is omega naught. Half the original spectrum is width is omega m. This is also omega m. So from this picture, we observe that omega naught is equal to 2 omega m exactly. There is no spacing between the repeated spectrum. So 2 pi f naught equal to 2 into 2 pi omega m, 2 pi fm, omega m is 2 pi fm. This is not, so 2 pi fs sampling rate is equal to 2 into 2 pi fm, because omega m is 2 pi fm, where I can cancel 2 pi on both sides. And here you observe that Fs is equal to 2Fm, which is called the critical sample case, where there is no spacing between the repetitions. Let's see case 2, which is what we say it as a oversampling case. Let me draw the spectrum in this oversampling case, that is xs of omega with original and repetitions. So we observe some spacing or some band, empty band that exists between the repetitions. Let me plot the xs of omega in this case. So this red color is representing the original spectrum of x of t in between minus omega m and omega m. And as usual, this black color spectra are the repetitions as per the mathematical equation we derived on both sides. But if you observe that there is a gap between the repetitions, and here the first repetition is centered at omega naught, second one at omega naught. And this is for k equal to 1, this case for k equal to 0. This is for k equal to 1, this is for k equal to 2. This is for k equal to minus 1, and this is for k equal to minus 2. And so on. All this continues. As we did earlier, so this distance is omega naught. Half the spectrum is omega m. In the repetition, this also is omega m. And we observe that the gap between the original and the first repetition. That means here omega naught is greater than twice the omega m. So following the same, 2 pi fs, that is the sampling rate, is greater than 2 times 2 pi fm, where fm is the maximum frequency. Let's cancel 2 pi on both sides. So fs is greater than 2fm. This is what we say it as a oversampling case. Let's go for the case 3, which is named as the undersampling case. Where the repeated spectrum here in this undersampling case overlap each other. Let me draw again the spectrum xs of omega. As usual, I'm using the red color for representing the original spectrum in between minus omega m and omega m, and the black color for the repetitions. But here you observe that the repeated spectrum are overlapping, and this continues, and even you can see on the left hand side even. This is centered at omega naught, 2 omega naught, centered at 3 omega naught, minus omega naught. This is centered at minus 2 omega naught, and so on. This is x of omega for k equal to 0. This is x of omega minus omega naught for k equal to 1. X of omega minus 2 omega naught for k equal to 2. And as usual, we measure this distance as omega naught from the picture. Now we observe that half the band is omega m here, and half the band in the repeated spectrum is also omega m. But here you have to observe that omega naught, as different from the previous case, is less than 2 omega m. Following the same notation, so 2 pi into fs is less than 2 times 2 pi fm. So let's cancel 2 pi on both sides again. So Fs is less than 2 times Fm, which is the undersampling case. This is what we observe, the overlapping between the repeated spectrum and the original spectrum is what we say it as a aliasing effect. What we say it as a overlapping. And here, the first overlapping and so on are represented as high frequencies, and the red color spectrum is observed as the low frequencies, and high and low frequencies are being overlapped. That means the high frequencies are taking the identity of low frequencies. Because of this overlapping, high frequencies are being observed or taking the identity of low frequencies. In this case, when I use a low pass filter for reconstruction, because of this aliasing effect, the reconstruction is not possible because the original spectrum is not being filtered out in low pass filtering option. Whereas in case 2, reconstruction is possible because when I apply the low pass filter, I can easily extract the red color spectrum, which you see on the screen. That is from minus omega m to omega m. Similarly, in case 1 also, reconstruction is possible because if I pass this through a low pass filter, I can easily extract the red color spectrum. That means I can easily get the original signal. So reconstruction is possible. Which is not the case in undersampling. So let's have a summary. So reconstruction of signal x of t from its samples xs of t is possible in 2 cases, as we have seen earlier. The case 1, that is a critical sampling case, and the oversampling case. And the reconstruction is not possible in the undersampling case. And I also want to mention that this sampling theorem is proposed by Harold Nyquist. So the sampling rate, what we are representing using Fs, which is equal to 2Fm in the critical sampling case, is also called as the Nyquist rate. And the inverse of the sampling rate, which is equal to the sampling interval, which is equal to 1 by 2Fm, is called the Nyquist interval. So critical sampling here means the required number of samples are available for reconstruction of x of t from its samples. Oversampling means more the samples, that is more than the required number of samples are available for reconstruction of x of t from its samples. Whereas the undersampling means the number of samples are less than required. Or less than the required number of samples which are needed for reconstruction. So in this case, the reconstruction is not possible. So this is all about the sampling theorem. Thank you.